Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at converting fractions to decimals. You're probably already aware that we can take a fraction like a quarter and we can write it as a decimal. A quarter and 0.25 are the same number. They have the same position on the number line. So one way that we can convert fractions to decimals is we can take a fraction like 3 over 5 and find an equivalent fraction whose denominator is a power of 10, because our system of organizing numbers is base 10. So 3 over 5 is equal to 6 over 10. So that means we have 6/10. So we can just write it as a decimal with a 6 in the tenths column. 3 over 5 and 0.6 are exactly the same number, just represented in different ways. Sometimes it's more useful to use fractions, sometimes decimals. But unfortunately, this method of finding an equivalent fraction whose denominator is 10, 100, 1,000, whatever, won't always work. If we have something like 4 over 9, it won't work because 9 does not go into any power of 10. There is no power of 10 divisible by 9, whether we're talking 10, 100, 1,000, or whatever. So in that case, we need another way that we can convert fractions to decimals. And the method I'm going to give you is short division. So remember, 4 over 9 is the same as 4 divided by 9. In other words, you're saying how many times does 9 go into 4? So when we're doing this, we'll put some zeros here because we know we're going to get some numbers after the decimal point. So how many times does 9 go into 4? Well, it doesn't go any times. It goes 0 times, remainder 4. Now, when you're doing this, very important that the decimal point is above the decimal point. So we've carried the 4. Now we say, how many times does 9 go into 40? Well, it goes 4 times, remainder 4. So how many times does 9 go into 40? Well, it goes 4 times, remainder 4. How many times does 9 go into 40? It goes 4 times, remainder 4. And you can probably see now that this is just going to go on forever and ever. Every time we're going to get 9 into 40, it's going to go 4 times with a 4 remainder. So this is what we call a recurring decimal. The numbers after the decimal point, called the decimal expansion, they go on forever and there's a predictable pattern. Every number after the decimal point is going to be 4 and it's going to go on forever and ever. So what we do is we write it as a decimal like this, 0.4 recurring. So what we do is we put either a dot or a dash above the reptend. We put a dot or dash after the digits that are repeated infinitely many times, that just go on forever and ever. Now it turns out this short division algorithm can also be used for decimals like this. We could have just done 5 into 3. Well, 5 doesn't go into 3 any times. It goes 0, remainder 3. Decimal point above decimal point. Now we go 5 into 30 is 6. So this here is called a terminating decimal because the digits after the decimal point, the decimal expansion eventually ends. It doesn't go forever, unlike 0.4 recurring here. So how do you know when a fraction is going to have a terminating decimal or a recurring decimal? Well, firstly, we need the fraction in simplest forms, which these two are. It's all about the denominator. Can the denominator go into a power of 10 evenly? Is the denominator a fraction of any power of 10? That's 10, 100, 1,000, 10,000, and so on. So it turns out that there will be a terminating decimal like these two when the only prime factors of this denominator are 2 and 5. So 4 is 2 squared, that's its prime factorization. 5 is just 5. So each of these has no prime factors other than 2 or 5. On the other hand, the prime factorization of 9 is 3 squared. It is divisible by 3. It's divisible by a prime other than 2 or 5. And when that happens, it means that the number will not be a factor of any power of 10, and consequently it will have a recurring decimal. So 2 over 11 will have a recurring decimal because 11 is a prime number. This number at the bottom is divisible by a prime number that's not 2 and not 5. So for 2 over 11, if we want to convert that to a decimal, we're really saying how many times does 11 go into 2. So again, we'll put some digits here. So put some zeros after the decimal point. So 11 goes into 2 0 times, remainder 2. Decimal point above decimal point. How many times does 11 go into 20? It goes once. 1 times 11 is 11, and there's 9 remainder. So how many times does 11 go into 90? Well, it goes 8. 8 times 11 is 88, and there's a 2 remainder. How many times does 11 go into 20? It goes once, remainder 9. How many times does 11 go into 90? It goes 8, remainder 2. When you're converting to recurring decimals, just stop when you see the pattern. You can see clearly here, every second digit is going to be an 8, and every first digit is going to be a 1. It's just going to keep going like this forever and ever. It's going to be 0.18181818. It will go forever. So the way we write this is 0.18, and we put a dash or dot over the digits that are repeating. These two here are called exact form representations. This is the exact form of 4 over 9, the exact form of 2 over 11. So what about 7 over 12? Well, let's look at the prime factors of 12. It's 2 squared times 3. 12 is divisible by 3. It's divisible by a prime number other than 2 or 5. Therefore, it will have a recurring decimal. 12 will not go into. 12 is not a factor of any power of 10. So we're going to do this similarly to the ones above. So 12 into 7. So how many times does 12 go into 7? It goes 0 times, remainder 7. Decimal point above decimal point. How many times does 12 go into 70? Well, 12 times 5 is 60, and there is a remainder of 10. So now, how many times 12 go into 100? Well, 12 times 8 is 96, so there is a 4 remainder. How many times does 12 go into 40? It goes 3, remainder 4. How many times does 12 go into 40? 3, remainder 4. How many times does 12 go into 40? 3, remainder 4. You can see we've now reached a pattern. The 3's will just keep going on forever and ever. We'll keep getting 12 into 40 is 3, remainder 4. So writing that in exact form looks like this. We have 0.583, but only the 3 is recurring. So only the 3 gets a dot above it. We don't put a dot over the 5 or 8. It's not part of the reptend. The 5 doesn't occur infinitely many times. The 5 and the 8 do not keep coming up in the decimal expansion. So 0.583 recurring just means 5, 8, and then the 3's, only the 3's go on forever. Alright, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.